Hello guys, today we'll be talking about energy levels and energy bands. So let's consider the structure of the atom. So let's say we have the neutrons and the protons here, that's the nucleus here. And we are moving from the center to a particular shell or a particular orbit. Let me add additional one. Okay. So let me make this one yellow. Okay. So for this thing, let's say this one is R1, this one is R2, and the other one is R3. So as an electron is moving from one particular orbit to the other orbit, the energy increases. So we can conclude that R3 has greater energy, has the greatest energy, the greatest energy. So R3 has the greatest energy, followed by R2, then R1 having the least energy. So the one with the smaller orbit or the radius of the orbit have the least energy as compared to the one with greatest radius of the orbit. So the larger the orbit, the greater its energy. So it becomes more clear that the outer orbit electrons possess more energy than the inner orbit electrons. So let's say electrons are distributed on this outer, and we also have other electrons distributed on this outer. We can conclude that the electrons which are yellow in color have small energy, and the one which are red in color have the greater energy. Yes. So the greater or the larger the orbit, the greater its energy, and the smaller the orbit, the smaller its energy. So let's take note of that. Also, so let me arrange this one in terms of a diagram like this, something like this. So let's say we have R1 here, R2 here, R3 here. So this is the first energy level, second energy level, and this is the third energy level. So we have the edge of the nucleus here. So let's say from here to here, from the edge of the nucleus from the edge of the nucleus to the R1, the distance there is small. So we can say that the energy there is small, and hence it has smaller atomic smaller orbits, and hence the energy level is small. When you get to R2, from the distance from the edge of the nucleus to that of the second energy level, we can see that it's longer than R1. So we can conclude that the second energy level is greater than the first energy level, and likewise the third energy level, it has the greatest energy level. So that's what I want to mean from this. Okay, let's get to ways of finding the energy bands in solids. Okay, so you start with the energy bands. In solids. So we consider some terms there. We have the valence band, we have the conduction band, we have the forbidden energy band, so we consider these terms. So let's start with the valence band. So the valence band, we know that the valence band comes from what is called valence electrons. Yes. So it comes from what we call the valence electrons. As we discussed, we said that the structure of the atoms, we have many shells. So let's say we have this nucleus, and we have shell 1, shell 2, and shell 3, and many more. So we can call this one as K. Let me start from the smaller one. So this one will be called K, this one will be called L, and this one will be called M. So KLM, shells. So the smaller one, K, then moves L, then moves M, and it goes and goes and goes. So this one is the nucleus that contains the neutron and the proton as usual. So you know that for the valence band, we said that the electrons are at the outermost shell is called the valence electrons. So at the valence band, we can say that the range of energies possessed by the valence electron is called what? The valence band. The range of energies. So the band means that what we can say is the range of energies. Yes. So the band particularly means the range of energies. So the range of energies which is possessed by the valence electrons is called the valence band. Yes. So I said the electrons in the outermost shell, the electron in the outermost shell. So let's say the one being red, they are called the valence electrons. And also the electrons in the outermost shell, they can be completely filled or they can be partially filled. So we can fill them completely or we can fill them maybe 3, 5 years. The outermost electrons. They may not be fully filled. They can be partially filled. So if they are fully filled, that means that there will be no free space for the electrons to move because they are fully filled. But if they are partially filled, there can be free spaces for them to move. So the electrons being able to move freely, they are called free electrons. So these free electrons will be moving. So as they are moving freely in the outermost shell or the valence shell, then they will result in conduction of current. So the free movement of electrons or the movement of the free electrons in the outermost shell result in the conduction of current. So we can say that, let's consider, so for the valence band, let me consider conductors or semi-metals. You see semi-metals, they are from group 1 to let's say group 3. That is, they have one electron in the outermost shell or two electrons in the outermost shell or the three electrons in the outermost shell. So for the valence electrons, they are more free, like they have three outermost electrons or two or one. So the electrons are free to move in the outermost shell. So since they are free to move, they are easily able to conduct electricity or current, because as the electrons are free, they result in the conduction of current. As compared to non-metals, non-metals can have 5, 6, or 7. So for non-metals, something like that, the electrons, even though it's partially filled, the electrons are not free because they are more at the they are the valence shell. So they are not able to move freely. So they are not able to conduct more current, even though they conduct current, but they are not able to conduct more current. Let's get to inert. When we come to inert gases like this, they have fully filled outermost shell. So that means that the electrons are not able to move freely because they are fully filled. So where are they able to move? They are not able to move. So that means they are not able to conduct electricity or current there. So we can say that for the valence band, when you're considering conduction there, so as I say, conduct valence band, conduction band can take place at the valence band, and I using conductors, conductors, and also semi-metals. That is um not semi-metal particularly, non-metals that are the insulators or non-conductors. And I was also using the inert gases as usual to classify or to verify the conduction band well. In the valence band, I said the electrons that are being located on the shell, the outermost shell. So they possess greater energy as compared to the one which are located inside of it. Yes. So we also get to the forbidden gap. So for the forbidden gap energy band, let me put the gap there. So for the forbidden gap energy band, so that one is the separation between the valence band and the conduction band. Yes. So let's say the electrons from the valence band, they want to move to the conduction band. Yes, they want to move there to conduct current or to conduct electricity. So the gap between these two, the valence band and the conduction band, is called the forbidden gap energy band. So if there is a huge gap between the valence band and the conduction band, the electrons are from the valence band, the electrons are not they are not able to move to the conduction band. Yes, because for the forbidden gap, there is no allowed energy state in that region. So there is no energy there. Yes. So electrons are not able to move from the valence band to the conduction band to conduct current. So those electrons are being tightly bounded to the nucleus, so they are not able to conduct current there. If you are being able to tightly bound to the nucleus, you're not being free to move to conduct electricity, and that restricts it to move to the conduction band. So let's draw the energy level diagram, energy band diagram. Sorry. So the energy band diagram. Let me use this. So let's say we have here, and we have this one too here. This part is called the valence band. And you have a valence band, and you also have the distance between them. That is separation between them. It's called the forbidden gap. Forbidden energy gap. So there is the band energy. So there is the band energy. Yeah. So that's the band energy. So the conduction band and the valence band. So the electrons are moving from the valence band to the conduction band to conduct electricity. So the greater the forbidden energy gap, the lesser the ability for the valence electron to move to the conduction band to conduct current. So that is very simple and more explanatory. So that's for the solid part of it. The same solid, that is for the conduction part of it, that the conductors part. And we can also consider it for the insulator. So we say that the valence for the conductors, the valence electrons are the outermost electrons. So they are free to move and they also help in conduction. So if they are free to move, they can move to the conduction band. And for that one, the forbidden energy gap will be small because since they are able to move to the conduction band, the energy there will be small. Let's compare it to the insulators. When compared to the insulators, we can say that for insulators, the electrons are not free to move. They are not free electrons because the electrons there, because we have many electrons at the outermost shell. So they are not free to move to get to the conduction band. And because of that, there is less current being produced. Not there is no current, there is less current. Current will be produced, but it will be small as compared to conductors. So we can conclude that the forbidden gap in insulators is very huge. So insulators, it has huge forbidden gap as compared to conductors, which has small forbidden gap. So because of that, we can conclude that the energy gap between valence and the conduction band in insulators is very large. So we can say they are approximately equal to 1.5 electron volts because then the energy is very large because the forbidden energy gap is very big. So they cannot cross from the valence band to that part. So for the valence band, it has full electrons, full valence electrons because the electrons are many there. For the conduction band, they are empty, empty electrons there because there's no crossing, empty electrons there. So if you want to cross, you need a very gigantic energy to move from the valence band to the conduction band. Otherwise, there will be no conduction in the insulator part. But for conductors, very simple because the energy there is very small. The energy there is very, very, very small. So they're able to move or the distance. Let me take it like that. The forbidden energy gap is very small, so it will require only small amounts of energy to move the valence electrons to the conduction band to conduct current or electricity. Also, when we get to the semiconductors as usual, the same thing applies. For that one, it is in between uh, metals and non-metals, that is insulators and the conductors. So if insulator has the biggest forbidden gap energy, semiconductors will have big, but it won't be bigger than the insulators. Yes. So because of that, for that one, they require almost 1.0 electron volts. The energy there, they require 1.0 electron volts. Yes, to break that energy so that they can move to the conduction band. So that's how to analyze the energy levels and the energy bands for metals, that is the insulators, conductors, the non-metals, that are the insulators, and the semiconductors, that are the semi-metals. Thank you for watching this video.